Good afternoon. My name is John Wordsworth, and I'm the Chief Architect at Paradox Interactive. I'm excited to have this opportunity today to share with you some insights into how machine learning is changing how content is generated in game development. Now, I'm a bit of a nerd, and I grew up in the 80s and 90s playing a lot of video games. Nostalgia aside, it still fascinates me today when I remember that the games we played back then typically fit onto a single floppy disk. In fact, the size of the background image on this slide alone is bigger than most of the games I played growing up. One of my favourite games was Frontier Elite 2. If you're a gamer around my age, you probably remember it. Elite 2 was a spaceflight simulator that contained hundreds of millions of star systems and tens of thousands of inhabited planets that you could actually land and visit. And of course, all of this in a game that fit into 880 kilobytes of storage space. Now let's be honest, machine learning isn't going to help us bring games down to 1 megabyte in size again. As I'm sure you're all aware, some deep learning models can get very large and easily stretch into hundreds of megabytes in size. However, machine learning is going to help us build richer, more realistic, and more expansive worlds in ways we haven't done in the past. Right now, I believe we're on an exciting frontier as we see new applications of machine learning appearing that will augment and in some cases perhaps completely revolutionize the ways that we build video games. I really consider myself very lucky right now, as I find myself in a position where I can use my research background with genetic algorithms and neural networks and combine it with my nerdy passion for game development. Now, the big question, of course, why should we care about machine learning when it comes to building and developing games? Well, there are three main reasons I can see for why we should be excited about machine learning in game development. First of all, it will allow us to increase the quality of the games that we build. Machine learning will power tools that will allow creators to automate parts of their process. This in turn will reduce the time that they spend on the mechanical parts of their job so that they can focus their time on what they do best. Reduced iteration times also allow creators to try out more variations of their content and add more unique flourishes and polish to their artwork. I think it could also have an interesting impact on the general happiness of creators too. Working with the latest tech and getting more time to spend on the fun parts is definitely a bonus. Secondly, as the technology matures, it will allow us to reduce the cost of certain aspects of making games. Some parts of the game development process are very costly, especially parts which require actors, such as recording voice talent or motion capture. When last-minute edits come in after recording has taken place, re-recording those new lines can require setting up another recording session. Finally, and this is what I'm most excited for myself, in the long run, machine learning will enable new and unique experiences for our players. By integrating deep learning-based features directly into games, we can offer whole new experiences to our players. For example, synthesized speech will allow us to speak the player's name in pre-recorded cutscenes, and generative networks could allow us to build customized worlds based on the player's unique profile. Facial recognition could also allow us to capture the player's emotional state and alter the game experience. Player is looking bored, for instance, you could add more action, although you might run into some ethical issues if you start capturing data on that. Before we go into the details, I want to give you a brief overview of the different parts of a game and how they are made. At the end of the day, a game is a piece of software. It takes a large collection of different types of data and content to produce an interactive experience for the player. Each of these different types of content is created by talented experts who have often spent years training in their specialist area. During the production process, they also need to work together to ensure their content matches the overall vision and design parameters of the game. Each discipline typically uses a suite of highly specialized tools to generate the different types of content that make up their part of the game. For artists, this could be hand painting images or shifting around vertices in 3D models. For coders, it's writing thousands of lines of C++, and for audio engineers, it could be recording and editing voice samples. While some disciplines will create their content from scratch, a good proportion of the content that makes up a game today is often based on real-world material. For instance, textures on 3D models are often based on real-world photos, and the dialogue that makes up cutscenes obviously use real-world voice recordings. The final result is typically an executable that runs on the client's machine, packaged with gigabytes of content that has been packed into a highly optimized format for the game to load as fast as possible. So, what do all these disciplines have in common? Well, at the end of the day, they are all essentially creating data for the final game executable to transform into a sequence of 2D images and audio. Sure, the game has to react to player input, but it's still all based on rules that make up the game's content. Every single part of what constitutes a game is essentially just data, whether it's the color values of the pixels in an image, the positions of the vertices that make up a 3D mesh, or the waveform of an audio clip. Still just data. I'd even consider source code and world scripting data as well. Both are typically just text documents at the end of the day. The great thing about data is that it contains patterns, and it's these patterns and that data that opens up the world of opportunities for machine learning. At this point, you might think that I'm missing something incredibly obvious. There are, of course, huge applications for machine learning with regards to the artificial intelligence that drives the non-player characters in a game as well. We've already seen in the news how modern techniques can be used to train AI that can beat human players in games such as chess and now even StarCraft. However, many games are not out to design a perfect AI that can crush the player. The interesting challenge is to make an AI that provides a realistic experience and a challenge that isn't too hard. Anyway, we're not going to touch on this topic today, but it's a very interesting field and I'm sure we're going to see it grow in the future. Now, I want you to think back and try to remember the first wow moment you had with machine learning, that thing that you saw that made you think, yeah, this is going to really change how we do a certain task in the future. For me, it was several years ago when I first saw style transfer in action. As several of our games are historical in nature, we often have actual source material from the real world that forms the basis for the artwork we create for the games. For instance, we might have portraits or even photographs of people and places that feature in our games. And so I thought, wow, this is going to be amazing. We're soon going to be able to convert photos straight into game art at the click of a button. This will let our artists spend more time adding polish and doing the things that make our game even better. Well, this is how it actually went a few years ago. As you can see, the initial results were a little bit disappointing. On the left, we see real in-game artwork for Winston Churchill, which was hand-painted over a photograph by an artist. On the right, we see an early attempt at training a style transfer model to apply the same style to the same source photo. Over time, however, the quality did get better, and we got improved results from the emergence of new research. However, the quality was far from something we could release, and the artifacts in the produced images typically meant that they also couldn't really be used as a halfway step to help artists either. For example, in the image here, the artist would likely need to redraw the whole image anyway, as the lines are too wavy and the sky is full of artifacts. On the plus side though, the content generated at this stage could still have some applications in the development process. In the early stages of game development, it's typical to use placeholder artwork in prototypes and early builds, and having placeholder artwork that's closer to the real thing is better than just having a pink box with text on it that says image here. Well, that was my journey of watching innovation around the field grow into inflated expectations and then sliding down into the trough of disillusionment. The picture today, however, is much brighter, and we are starting to see several technologies move up along the slope of enlightenment, especially as some companies are looking to commercialize many of these techniques into products. This is what makes it such an interesting time to be a part of this field. Some of the techniques that I see as moving up the slope of enlightenment right now are dynamic image upscaling, which allows for higher resolution gameplay upscaled from a lower resolution source image. This means that gamers can play at 4K even if parts of the game are rendered at 1080p without a huge performance cost or loss of quality. Otherwise, speech synthesis and lip syncing 3D models to pre-generated audio files are also reaching new levels of maturity. There are still a number of technologies moving through the inflated expectations and trough of disillusionment. It's incredibly hard to generate 3D models, for instance, that match the artistic style and quality of the game you are building. While GPT-3 is impressive at generating paragraphs of text, game designers typically have a story and writing style of their own, and part of the craft is in the human factor of having everything fit together neatly. However, it's also still an exciting time in terms of innovation. As we see some technologies commercialized, there is still a fertile field of innovation open to developers in generating worlds or using game-specific applications to provide unique player experiences. Next, we're going to take a closer look at 3 direct examples of the applications of machine learning in content generation. A quick disclaimer before we deep dive. I have to emphasize that these are all internal experiments at this point, so if you do happen to be a fan of our games, please don't expect to see these coming in future updates. In our first example, we revisit the work of the 2D artist. The portraits of historical figures in our World War-focused game Hearts of Iron are hand-drawn images based on real-world photography. Upon returning to the problem with lower expectations, instead of expecting a single neural network to take an input photograph and produce production-ready artwork, it was clear that better results would be achieved by breaking the process down into a number of discrete steps. Here we see how a chain of different techniques can be used to generate a stylized version of Winston Churchill. While the final image still doesn't match the style of the artwork used in the game, we can see that it's developing a style of its own. So what's actually happening here? We start by running the source photograph through a denoising network, as old photos tend to be grainy, and this grain can produce unwelcome effects when applying style transfer later in the pipeline. The next step uses an interactive colorization technique based on the 2017 paper, Real-Time User-Guided Image Colorization with Learned Deep Priors. This technique helps colorize old black and white photos, but also allows the user to provide color hints for areas of the image, such as the color of the bow tie or the skin color of the face. After removing the background using Photoshop, style transfer algorithms provide additional layers of detail, which are then all blended together with different weights into the resulting image. The main takeaway here is that while we might not be able to generate a pipeline that can precisely replicate features or artwork in our existing games, future games should consider how their pipelines could be rebuilt around machine learning techniques. By creating new art styles and pipelines from scratch with machine learning in mind, instead of trying to adopt new technology to old methods, new approaches will offer new opportunities in all areas of content generation. Here's just another example of a completely different type of artwork that can be created using a similar sequence of techniques. This example is particularly interesting because the line art which is generated is in a state where an artist could continue to work on and perfect the image, or even combine elements from several different images into one final composition. For our next example, we're going to look at the recent advances in speech synthesis or text-to-speech. Recording dialogue for a video game is a costly process which requires audio engineers and actors to spend several hours or even days in a studio environment recording pre-written dialogue. What's worse, in the event that last-minute script changes come in after recording, it can be very costly to make minor edits to existing audio. Not only might it be necessary to re-record the source audio, but if the edit has come in very late in the release process, you might also need to fix all of the translated versions of your audio as well. Speech synthesis using deep learning enables high-quality reproduction of actors' voices based on a pre-built voice-specific model and text. Such speech synthesis solutions are already being commercialized, as they have several applications outside of the gaming industry. While speech synthesis is still some way from completely replacing voice actors who can bring a wide range of emotions and character to their recordings, the technology is still very impressive today. Where games are using heavily filtered voices, such as a robotic voice used for an advisor or tutorial agent, this technology is able to produce great results. Here is an example of a recording from one of our games.
We should now be ready to extend our great civilization to a second world.
Here is an audio clip generated using NVIDIA's Flowtron after fine-tuning the voice to match my own and then applying some filters.
We should now be ready to extend our great civilization to a second world.
And, as mentioned, there are some great strides being made at this time to commercialize such technology, and it would be remiss of me not to mention the quality of these tools today. For example, here is an audio sample which is completely computer generated from my voice print using a tool called Descript. Here is a sample of a completely synthesized sentence based on my voice. Training a model for speech synthesis requires a combination of text transcripts and audio files to build a model specific to the actor and voice style. When building such a model, the audio files need to be carefully cleaned, removing noise and silence at either end, and the text transcripts require attention to detail to ensure that they match the audio. Training a high-quality model from scratch requires 10 or more hours of audio content and transcripts, ideally cut into small 5 or 10-second clips. After this, the training process can take a day or more on even the best available hardware. Fortunately, good results can be reached by taking a pre-trained model and fine-tuning them with a custom voice to continue and finalize training. But even then, capturing 15 minutes of data and running several hours of training still leads to a slow iteration time overall. At a high level, model training for speech synthesis tends to work by segmenting and extracting audio features from the input speech, while also breaking down the input text into phonemes. A difficult challenge in and of itself. This data is then used to synthesize new samples to compare against the validation data. Speech inference is also a multi-stage process where input text is broken down into phonemes and used to generate a spectrogram using a trained synthesis model. This spectrogram is fed into another model, which is used to generate the final waveform. In the short term, deep learning generated speech synthesis provides a unique opportunity to capture the likeness of the original actor to make changes and fill in missing audio samples without having to re-record the original actor. In the midterm, I expect smaller game studios or bigger game studios with highly filtered voices, i.e. robot voices, to use deep learning to generate voices to replace actors in their games. In the long term, as the quality of synthesized voices continues to improve, it's likely that many studios will be able to replace some of their voice actors with synthetic voices. Existing solutions already allow you to save multiple different moods or emotions for a given type of voice, and then shift between them. And these modifications are only going to keep improving over time. At the current level of quality, the technology already has interesting applications to also improve accessibility in games, from reading out tutorial text that might not otherwise have been recorded to reading out chat messages that come from other players in the form of text. Lastly, I want to share an example of how machine learning can be integrated even tighter within a single game using custom solutions tailored towards that specific game. These types of advancements can support creators working with custom solutions and even provide new and unique experience for players if bundled with the game itself. While our older games use 2D images to represent the characters in our game world, our more recent games use 3D models, which are highly customizable to represent characters in the game world. Our portrait engine dynamically generates the 3D meshes, like the ones you see here, from over 100 parameters or genes. Each parameter typically controls a different facial feature, such as the space between the eyes, the thickness and height of the eyebrows, or the width of the jaw or the chin. This means that there is a huge variety in the types of faces that we can generate, and while many of these faces will be very similar, the space of different possible combinations of genes is huge. Under the hood, each portrait is represented by a DNA sequence, which can be represented as shown here with a base 64 encoded string. Believe it or not, however, even with this number of faces, it can be difficult to exactly reproduce the face of someone from the real world, and with so many options available, the process of recreating the face of a historical figure can take quite a long time, as an artist needs to manually tweak and adapt these parameters until the face matches the reference images. Using machine learning, it was possible to create a tool which could take a photograph of a person in the real world as input and then generate the DNA string which would build a portrait of that person in the game, based on the photograph that was provided. Due to the historical nature of our games, it was great to see that the technique also works pretty well from high-quality portraits, and it doesn't perform too badly on photographs of statues as well. It's not perfect, but it generally gets to the point where only a handful of genes need to be fine-tuned to produce the desired result, instead of hours of time spent building a character from scratch. It could also be possible in the future to build this in such a way that the user could import a photo of their own face, adding a new experience to the game that would be difficult to create before machine learning. We start the process of generating a face match by selecting a photo of the target. As there are a limited number of hairstyles in the portrait engine, it's sometimes hard to find a close match, and so we also start by selecting the closest or a stylistically similar hairstyle and a beard as a fixed parameter. The next step is to generate a random pool of DNA, and then each DNA string is used to generate a static image corresponding to the face. A neural network is then used to extract a set of numerical values for each face, where the values encode certain facial features, such as the distances between the eyes or the space between the eyes and the mouth. The fitness of each face is then assigned based on the distance of the profile generated from the profile of the target face. The population is then sorted on fitness, and the bottom 80% of the population are removed and then regenerated using a mixture of crossover and mutation steps from the top-rated DNA strings of the previous generation. The process continues until we see no practical improvement in the fitness function for 5 sequential generations. A genetic algorithm was used for the generative phase of this process to account for the fact that the components that make up a face can be changed at runtime. Different games, and even our players, can add new genes and facial features to the game. While a deep learning model might be able to produce better results faster, changing the source material would likely require retraining of a model, which is not something we can expect our creators and maybe one day even users to do while generating content. The two main takeaways I see from this experiment are, firstly, we are just scratching the surface for ways that machine learning can be used to not only support our content creators, but even potentially adding new features that will add value for our players. Secondly, while genetic algorithms are no longer cool, I still think there's a lot of potential for using them alongside deep learning and neural networks. At a simple level, a genetic algorithm can be useful for both replacing the content generation steps in some other algorithms, but I can also see applications of using genetic algorithms to fine-tune hyperparameters in existing systems. While I'm certain that machine learning and deep learning are going to change how we build games in the coming years, there are still some challenges to solve before we get there. Training deep learning models presents a number of interesting challenges. First of all, several of these models require a large amount of data, which needs to be gathered, cleaned, and prepared for use. Secondly, the hardware and time required to train certain models can make it iterating and experimenting with different structures and hyperparameters slow and tedious. As an example, when working with NVIDIA's Flowtron, which in itself is faster than its predecessors, training a voice from scratch requires 10 hours of audios and several days of training time. Fortunately, there are some shortcuts available for making this process easier, but it's still just an example of the overhead that can come with building and maintaining such models. Building tools that can directly solve specific problems being faced by our creators also requires a multidisciplinary team to come together and work together. These teams typically require a domain specialist who understands the problem in enough detail to define the biggest challenges that need to be solved, a machine learning expert who understands the different techniques that are available in the field of AI to tackle that problem, and a programmer to build the tool itself in such a way that it can be used as a standalone tool with minimum maintenance. All of these skill sets are in high demand. So even if you're able to find and hire the right people, they will also be in high demand across the organization to solve many other short-term problems. While a wide range of tools in Git repositories can make it quick to start experimenting with machine learning, there are also a number of organizational challenges when it comes to perfecting a prototype and taking it through to completion. The fast-changing nature of the field means that solutions are often fragile and awkward to use. Solutions deployed to creators are often built on fast-changing Python dependencies, making tool usage frustrating and difficult. On top of this, integrating these new techniques often requires fundamental pipeline changes within the organization. To get the most out of machine learning, we will need to change our designs and pipelines instead of just augmenting them. So, in summary, machine learning is undoubtedly going to change how we build games over the coming few years and will help us to increase quality and reduce the cost of our games. In order to get the highest value out of machine learning techniques, we need to not only adjust but also rebuild some of the pipelines we use to build games today. And when we start to design content and pipelines around machine learning techniques, we will not only get the greatest value from them, but also be able to provide new and unique experiences to our players. The field as a whole is moving fast, and we are already seeing several of the techniques that were experimental just a couple of years ago moving into commercial application. It's going to be important to keep up to date with new trends when making build versus buy decisions around machine learning. But there are going to be some hurdles along the way. Many of these techniques are still suffering from increased hype, and will promise more than they can deliver until they are perfected. Oh, and I mustn't also forget to say, genetic algorithms are still cool.